Okay, good morning, welcome everyone to another webinar of our Particle and Astroparticles channel. Today we have Miguel Nebot from University of Valencia. Miguel got his PhD from University of Valencia, and he's been a postdoc at several institutions since then. For instance, INFN in Rome, Instituto Superior Técnico in Lisbon, and University of Valencia. His research area is physics beyond the standard model, with emphasis in flavor physics, CP violation, and Two Higgs Doublet Models, among others. And today he's going to talk about electron and Muon J-2 anomalies in Two Higgs Doublet Models. So I would like to thank you, Miguel, for accepting our invitation to give this talk. And yeah, feel free to start your presentation. Thank you.
Thank you very much. My pleasure to accept this invitation. And as you were mentioning, I'm going to talk a little bit about these electron and muon J-2 anomalies in a rather popular class of beyond standard model scenario, which is just Two Higgs Doublet Models, and in particular in a set of them which are just flavor conserving. So the outline of the talk is pretty simple. I will just briefly motivate why are we interested in this, if it needs some motivation. Then I will just review a little bit of these Two Higgs Doublet models to focus in particular on what are the properties of the couple of interesting cases which we will be using to address those anomalies. I will discuss in some detail the contributions that these models have in order to explain those anomalies. I will just briefly discuss when one wants to perform a full analysis of the situation. What are the constraints that are relevant in order to really gauge if these models can explain these anomalies without conflicting with a huge amount of evidence elsewhere. And then I will show some of the results that were obtained in this kind of analysis. This is based on work done in collaboration with Professor Botella and this PhD student Fernando Cornet here in Valencia. It's mainly based on this paper from June and relies to some extent on this kind of scenario relies on the previous paper with the same collaborators. So, well, what's the motivation? The motivation is that we have these two anomalies in the anomalous magnetic momenta of the electron and the muon. By anomalies, we mean that the experimental value deviates from the standard model expectation in both cases at the level of 2 to 3 sigmas, which means that combining them, we are there between 3 and 4. So if one just takes this as a hint of in physics, because I mean standard model is not able to explain that, well, one has to try to address what is going on. So these anomalous magnetic momenta are just related to this coefficient in general form of the electromagnetic interaction of charged fermion with the photon, of course. And of course, when you see that we are at this level, these observables are at this 10 to the minus 9, 10 to the minus 13, one sees that, well, since the early Schwinger alpha over 2 pi computation to nowadays thousands of 5-loop diagrams appearing in the anomalous magnetic model of the electron, there has been a lot of progress, not just theoretically, but of course experimentally too. So now focusing on these observations, one of the remarkable things, which is in fact quite challenging, is the fact that the deviations in both observables have opposite signs. So one can, well, naively translate this numerically into this ratio, and let's say translate it in terms of a ratio of the masses involved, of the fermion, of the electron and the muon. And you see that this, apart from this sign, is something which has this weird power of something like 3/2. And this is quite challenging, first thing, because we have opposite signs. So for many new physics solutions, many scenarios in which one wants to reproduce both anomalies, this different sign is quite challenging. But not only the sign, the fact that we have this peculiar value here means that, for example, if one has a new physics model in which the corrections scale, let's say, like the mass of the lepton square, well, this is already telling you, for example, that you will never be able to reproduce both, because simply the ratio of this kind of contributions is just off what you expect. So somehow the origin of both anomalies, with the hypothesis that it is beyond the standard model, we need some kind of effective decoupling in between what you are doing with the electron and what you are doing with the muon. Nothing naive like just proportional coupling, couplings proportional to masses or squares of masses will work. And we will address this in a context that I have already anticipated, which is two Higgs doublet models, which is quite popular. And the bottom line is that, well, in principle, one has a new bunch of couplings, and through them, one might try to play this game. So if one then starts to list, anticipating a little bit some of the things that I will present with more detail in a few slides, the simplest two Higgs doublet models, which are those symmetry shapes type 1, type 2, X or Y, in which the new couplings are always proportional to the masses. Well, this is already telling you that that will not work here. If one relaxes a little bit those impositions, you have, for example, those aligned two Higgs doublet models in which you still have proportionality of the new couplings with the masses. And again, this will not work. I beg pardon, but I lost all the references in the presentation, so that's a pity, but they are not so critical for the content. And finally, remaining in the simplicity of models in which there is flavor conservation, one can go to a more general scenario, which is the one within which we will be working. We'll see this in a few slides. So just to fix a little bit of notation, in general, when one is dealing with two Higgs doublet models, the Yukawa sector, which is the one we are, of course, the one we are interested in order to explore those anomalies, has this typical structure in which for each type of right-handed singlet fermion, you have a pair of Yukawa matrices with the couplings, and your one for each of the scalar doublets. So you do as usual, you expand around the vacuum, since you need to break electronic symmetry when there are waves around. And the canonical thing to do, first one goes through these Higgs bases, in which what you do is essentially put all the vacuum expectation value in one of the doublets, so the other is waveless. And there you read, for example, what are your Goldstone bosons. In the case of two Higgs doublets, this already isolates what is the physical charge scalar that you will have. And in general, you are left with three neutral scalars, which are not necessarily the mass eigenstates. So you still need to work a little bit on that neutral sector. So first thing, you go to these Higgs bases, and now your couplings have this aspect there. And you start to isolate what will be the fermion masses. Since this first doublet is the one that is getting a wave, the masses will be proportional to those matrices, which you will need to diagonalize, and you do that as usual. So at the end of the day, you have your diagonal mass matrices, those M's, and the second matrix with additional couplings. These are the new flavor structures, the one that we will need to play with in order to explain the anomalies. Fine. And here we're rewriting both. There are the Yukawa couplings in the initial, initial with basis, and then after going through the Higgs basis and the fermion mass eigenstates. And this, of course, is a question that arises already with the proposal of Two Higgs Doublet Models in 73. You have to care about flavor changing couplings. And natural flavor conservation, as put forward by Glashow and Weinberg in 77, re-isolated how a simple recipe to eliminate flavor changing couplings, which is through, for example, those two symmetries, and this gives rise to this type 1, 2, X and Y, Two Higgs Doublet models. And the bottom line there is that, well, by removing one of the Yukawa matrices in each sector through this symmetry, of course, you end up distributing the remaining one among those two matrices, which is telling you that at the end of the day, those new couplings are proportional to the masses. And of course, as we were anticipating, this is the kind of situation in which you will not be able to address these anomalies.
Miguel, may I ask a question? So this Lagrangian is written in the Higgs basis, right?
Yes.
What's the big advantage of using the Higgs basis?
That you already isolate what is the mass matrix and what will be the second flavor structure, those N matrices, which have the new couplings. Mm-hmm. Of course, you still need to identify which are the real mass eigenstates in the scalar sector.
The neutral.
Which, when you go to the Higgs basis, you have already isolated your Goldstone bosons, your charged scalar, but there are three neutral scalars which are not mass eigenstates. So this means that in principle here, in these couplings, at least for the charged scalar, are already completely defined in terms of the good mass eigenstates, charged scalars and fermions. But for the neutral scalar, you still need to work a little bit around. Mm-hmm. But everything, all the information is already here. Okay. Well, not all, in the sense that to define what are your scalar mass eigenstates, you need to provide some details concerning the scalar sector, and that we will see in a few slides. Yeah. So what I was mentioning is that beyond this natural flavor conservation, one can still keep the simplicity in these new couplings in terms of not having flavor changing coupling with the neutral scalars, with this kind of aligned to Higgs doublet model, in which just there is some proportionality, but with a parameter which is independent. I have not yet introduced what is this sub beta, which in the end will be tan beta, and that is related to the scalar sector, but this is fixed outside the Yukawa couplings. In this aligned scenario, you have an arbitrary parameter for that proportionality, and as we were mentioning, this we can already anticipate that will not work for the anomalies, but this has a virtue which is to keep in mind, which is that even if this kind of assumption is unstable in the quark sector when you analyze the renormalization group evolution, in the lepton sector, since here we are completely removing, we are just keeping massive charged leptons and massless neutrinos, in this simplified lepton sector, this kind of assumption is already stable under the renormalization group evolution. Well, one can give further steps in terms of generality and just assume that in order to keep flavor conservation and avoid a lot of problems associated to flavor changing couplings, the most general thing that one can think of is having just diagonal N matrices. This again is something that, well, is not stable in the quark sector, meaning that the renormalization group evolution does not keep a diagonal form of those matrices. I mean, off-diagonal terms will appear just out of this running, but this is stable in the lepton sector. If you assume that this matrix here is diagonal, the renormalization group evolution will not produce off-diagonal terms, which is nice. So what we will do is we will just choose a kind of combination of situation in which for the lepton sector we will just assume the most general diagonal form for this matrix, and in the quark sector we just keep the simplicity of this kind of natural flavor conservation, which gives you two different possibilities. Having this proportionality, and we'll see now in a moment what is this, as I mentioned, this parameter. So you only have two options there for the quark sector, and you keep the thing as general as possible in the lepton sector. So this one will be the general lepton flavor conserving model. One, because it has the same quark sector couplings than two Higgs doublet models of type 1 and also of type X, but that's around now. And the second model in which the dependence is different in the down sector. This one is the same as two Higgs doublet models of type 2. Good. So the thing is that with this matrix, diagonal, arbitrary, and stable at one loop level, the renormalization group evolution, the thing is that the couplings of the electron and the muon, well, are parametrically independent just by construction. And that is the kind of effective decoupling that I was mentioning before, that we will at least need to try to explain those anomalies. So this is the basic ingredient for the game. And now we need to just complete a little bit this model, and that means defining, completing the scalar sector. And since we are adopting these type 1 or type 2 UCA couplings in the quark sector, well, we will just extend that kind of Z2 symmetric situation to the scalar potential. With the only exception that, well, we just keep in mind that we may need to softly break this symmetry. Which means that in operators of dimension 2 or 3, violate terms which violate the symmetry would be acceptable. Good. So having defined the scalar potential, next thing that one needs to do is identify what are the physical neutral scalars, which are the only ones that are not yet well defined. Those are these small h, capital H, and capital A, and you obtain them from the fields that appear in the Higgs basis just through an orthogonal rotation. This is just the generic notation. And in terms of those fields, we will have the final UCA couplings, flavor conserving, of course, which will have this typical structure in which, in the end, we factor, as in the standard model, that kind of fermion mass over vacuum expectation value, and a couple of scalar and pseudoscalar terms in the coupling. So this would be the most general thing to do, but in fact this is too much, in the sense that even with a reduced amount of ingredients, that is introducing additional simplifications, we have enough to address those anomalies. So those simplifications that we will be adopting in the following is that, well, I will assume that there is no CP violation in the scalar sector, and that those new couplings, those ends in the diagonal, in that capital N matrix, are just real. And those two things are in the end related. So first, this first ingredient simplifies that mixing here that related the physical scalars to the ones appear in the Higgs basis to this simple form with just one parameter. So this leaves you, for example, with this third scalar here, since it does not mix, to be a pure pseudoscalar, and just one mixing involving the guy that you will try to identify with the Higgs and another neutral scalar, both scalars, not pseudoscalars. And that's it. Convention here is to use this alpha minus beta angle and having here sines instead of cosines. This is pretty weird, but the thing is, it's just a simple one parameter rotation, and that's it. In particular, in terms of this matrix, when this matrix tends to the identity, this is what is called the alignment limit, in which by construction, this small h will have the same couplings as the standard model Higgs. And this this is a limit to keep in mind when you want to see how things are working. Good. So the thing is that when you do that, for example, there are problems that you avoid, that I will mention briefly in a moment. So with those simplifications, those generic couplings that I was listing there, were simplified to this kind of combinations. You have those mixings and this parameter here, which is I'm going back because too bad that I have skipped that. Which here, where did I introduce this beta? Well, beta is the ratio of the vacuum expectation values. So this parameter here is the tangent of that. Here it is. Sorry. Here it was. I mean, the tangent of beta, which is just the ratio of the vacuum expectation values, is controlling here those linear combinations which appear in the scalar or pseudoscalar parts of the couplings to those neutral scalars. In the quark sector, everything is controlled by the mixing in this matrix and this ratio of vacuum expectation values. And the thing, as I introduced before, is that the only difference is that in going from the up to the down sector and going from model 1 to model 2, there is a difference in the tan beta dependence. And that's it. So the new parameters here do not play a role in defining these couplings, but we have two different dependencies in terms of tan beta. In the lepton sector, where all the new parameters reside, with this simplification, well, we just have those real parts, which in one case are distributed among the Higgs-like scalar and the other neutral scalar, and completely control the pseudoscalar couplings of this guy A. So those are the ingredients. And of course, the thing with this absence of CP violation that I was mentioning, which strictly means that the product of the scalar and the pseudoscalar coupling are zero. Either you have pure pseudoscalar or pure scalar, means that you have CP conserving couplings to a scalar. When you have this, what you are avoiding immediately is trouble with the electric dipole moments. The electric dipole moments arise from a similar operator than the anomalous magnetic moment, except that there is an extra gamma phi in your operator. So in this, in the standard, the electron EDM is quite constrained. So in principle, by just simplifying the game and assuming those real ends and no CP violation in the scalar sector, even we have less freedom to play around, we are absolutely safe from this point of view. So one can indeed relax that and gain some additional freedom, but since in the end it will not be necessary, we are happy with this. Then, of course, on top of the neutral scalar, you have the charge scalar, and we will need to keep track of what is going on in terms of the couplings for the constraints that would be playing in the end. Good. So with these ingredients, one needs to see how can I produce, or which kind of new contributions will I have in this anomalous magnetic moment. Well, the full prediction has a standard model piece, which is the one in which, for example, in the case of the electron, you're already including thousands of 5-loop diagrams, but that's the piece we are not interested in. Of course, we are just referring to the difference in between state-of-the-art theoretical predictions and the experimental values. So we are, of course, focusing just on what are the corrections that arise in these models. Of course, the aim is, well, I have predictions in these models that match the deviation in the experimental measurements. Of course, in these two cases. So what I will do in the next few slides is, well, rather than jumping into full details of an analysis, I will just analyze in a simplified situation if we can, what can we expect in these two models. So first thing in order to do that is, well, I will introduce these auxiliary quantities, in which I just factor out typical things that arise from your loop calculations, which are those 4 pi square factors, masses of the leptons over the BEVs, and this number here. So the thing is that when you do that, you realize that for the electron and for the muon, this is already giving you what is the size of the anomalous magnetic moments there. So your aim is to obtain these numbers which match the experimental values, and substituting things, what you are aiming is, but in the case of the electron, over this naive one loop thing, is to get that number, and for a muon, this one. And the ingredients in order to try to do that are, since we have those scalars, one loop diagrams with neutral scalars, which have this shape, and with charge scalar, just these other ones. I mean, you can couple the photon either to the charge lepton here or to the charge scalar there. And this is just what you have at one loop. Of course, is well known. The thing is that when you are at one loop in this kind of diagram, you are paying twice the price of coupling a light lepton with a scalar. And this is avoided in those two-loop diagrams of this bar C type, in which you are just having one coupling of a light lepton with a scalar and paying the price of an additional loop, having here the coupling of additional fermions. So if you think of couplings which scale with the masses, it means that you are saving here one light mass, paying the price of one loop, but having here a larger fermion mass. So that's why those two-loop diagrams typically play a role in many of these analyses. So we'll now take a look to, well, what happens with one-loop contributions and what happens with two-loop contributions in these models. So to simplify a little bit this initial analysis, the thing is that we go to the leading terms, expanding in the light lepton mass over the scalar mass, and this alignment limit in which there is no mixing in the scalar sector. And this is the kind of thing that you get. This simplified expression in which these functions here come from the loop. They have this form here. And the extra ingredient is that we are assuming that these new scalars are heavier than the Higgs. There are alternate situations in which you can try to address those anomalies with light scalars. This has different complications. The constraints that you will need to consider are different. But here we are focusing on a very simple situation in which, well, the Higgs is lighter than the other scalars, period. Well, so now we have at one loop this kind of contribution from a neutral scalar, pseudoscalar, and charge. And the typical values of these arising from these loop functions in this limit, in the leading contributions, is that this is the order of 20-something or around the 14 to 18. Case of electrons, case of muons. When you take these scalars in this wide range. So there is not much room in terms of the variation of these functions. And the next important thing is that one looks at the signs of the different terms, because you see that, for example, here there is a relative sign, and that is absolutely relevant in order to address the different signs in in the anomalies. So,
just a quick question. In the case of new scalar larger than the Higgs, would you expect a bigger contribution to this delta L because the mass goes in the denominator?
Yes, that is true. Absolutely. The thing is that you will later run into problems, for example, with data coming from lab. The simplest trouble that you will find immediately is that, well, at lab you were exploring E plus E minus going to whatever you wanted, and if you need here some scalar that couples to electrons and also couples to muons and has a mass which is below the Higgs mass, well, you might have a lot of trouble evading the bounds that come from lab, since you would have produced that resonantly. So we just avoid that kind of situation because there are additional, you may have additional complications, but this is the simplest one to see, that in that case you would be able to produce in the S channel that intermediate scalar, since typically that would have non-negligible couplings to electrons and muons. This would have been seen like a resonance in E plus E minus going to mu plus mu minus. Okay. So from that point of view, we go for the simplest thing, which is these guys are heavier than the Higgs, and we'll see. So the thing here is that with these numbers for those functions, the terms that can dominate here are the ones made by the scalar or the pseudoscalar. I mean, these numbers arise from the fact that we have this logarithm here, which we do not have for a charge scalar. So, for example, if one wants to address the electron anomaly, well, just because of the sign, the scalar cannot make it. It should be the pseudoscalar. So if you want to say, well, let's see how does the pseudoscalar work here. Well, I have here I just kept the generic thing, but I'm just focusing on in the case in which this is real. Otherwise, that would be an absolute value. What I need is that this number here is reproduced by this combination. So this means that if the function is this size, roughly speaking, this coupling should be this real of the NE should be like the mass of the pseudoscalar. So that is definitely a problem. This means that you will need to put, since you want this guy to have to be heavier than the Higgs, well, this means that you are putting here quite large numbers. And this might be a problem if you later impose some perturbativity requirement on your couplings, apart from other constraints like the one that I was mentioning. So in principle, for the electron anomalous magnetic moment, this does not seem to work at one loop. On the contrary, for the muon, since you need here just a 1 instead of a minus 16, it's not the pseudoscalar, but the scalar in this case. And because of the 16 difference, well, not the mass, but just 1/4 of the mass. So this means that a not too heavy scalar, while keeping a reasonable perturbative in mu, might be sufficient to do that. And, well, the pseudoscalar should be heavier in order to avoid cancellations that spoil this business. So in principle, the Muon anomaly might be feasible at one. Good. So that's for one loop. But what happens with two loop contributions? Of course, I'm just in the same approximation, leading terms in the like lepton mass and the alignment limit. Well, the two loop contributions have this generic structure in which the dependence on the lepton couplings now is linear, which is what we had here. And here it will be quadratic because you had it twice. Here it's just linear. And this additional factor collects information from the loops and the scalars that connect the external fermion line with the internal fermion loop, in the couplings, and of course the masses. So in these two models, this factor takes this form. And now we have these F's, G's, which depend on the fermion inside the loop, on the scalar connecting that. But the thing is that these functions here, F and G, well, first, they are very similar. In fact, the difference is just 1/10 of each of them, so they are quite close. And, of course, they vary a lot, depending on the argument here, which means that depending on how large is this argument, when the larger is the function, which means that, as we see in this couple of plots, well, the most relevant terms will be the ones which involve the heavier fermion, which is the top quark in that internal loop. I mean, going from top to bottom, you see that you are already losing a couple of orders of magnitude. In here for light masses, but it's close to 3 when you go to much heavier scalars. So this means that for a very simplified understanding of what is going on, just keep the top terms and see what happens. So if you just consider the top quark terms, first guess of what might happen is, well, take this tangent beta of order 1, take the neutral scalar with similar masses, and then one realizes that with the function that I had here, that for masses in that range, 1 to 2 TeV, one can indeed reproduce this electron anomaly with couplings which are, modest in the sense that modest compared to the electroweak breaking scale. This is still much larger than the electron mass, but just a few GeVs looks like a sufficient coupling to reproduce this. Now the thing is that since in this guess, it's just the top quarks that are doing that, which appear here. This kind of term. As you see, this is something which does not depend on the external lepton, be that the electron or the muon, and in fact it's the same in both models. 1 or 2 in terms of the tan beta dependence. And this means that in order to get the muon anomaly, you can use the same terms. The only thing is that you will need to modify to take a different value for the muon coupling. And you get that value just by comparing what if you reproduce the electron and you want to reproduce the muon and you have that scaling, well, it's just taking a muon coupling which is minus 15, 16 times the electron coupling. And that automatically gives you the good muon anomaly. And just the fact that you have different signs is just that the signs of the couplings are different. And that's as simple as that. So with those values here, this means that the muon coupling should be in that range, which is large, but not ugly in the sense of being larger than the Higgs wave, for example. So it's not that problematic from the perturbativity point of view. And as I was mentioning, this applies for both models. Good. If one wants to go beyond this initial assumption of order 1 values of tan beta, one needs to remember that when you go to very small values of tan beta, then you run into problems with some flavor observables. Because gamma and B mixings kill you. So in principle, this is a regime which is forbidden by other constraints in type 1 and type 2 Higgs doublet models. So the only remaining regime is large values of this. And what happens in this case? Well, with respect to this naive situation in which I was taking tangent beta 1 and those masses in that 1 to 2 range, I will take let's say, if I want to see if tangent beta 50 works, well, I know that for some values, like those ones, the thing work. So what should I modify if I want to make tangent beta 50 work? So take for definiteness, the first model, and you see that in this F factor, well, now you are putting a 50, a factor of 50, suppressing the dominant terms. So you will need to compensate for that. So if you want to compensate for that, you will need smaller scalar masses and also larger lepton couplings. So, for example, by reducing the masses to these 200 GeVs, which is a factor of 5 to 10 with respect to this reference value here, you already recover a factor of 10. So the rest, you can make it just with the couplings. So in principle, it looks like you can still reproduce this anomaly with those two loop contributions in that large tan beta regime, at the price of having lighter scalars and larger couplings. Can you extend this to the muon case? Well, in the muon case, this factor of 5 in the coupling is already quite problematic. So that might be something that you do not want to see. But as we have seen, one loop contributions were good for the muon. So this means that, well, this large tan beta regime works fine for the electron. It would work fine for the muon if I had very large couplings, but in fact I do not need them because one loop is sufficient to get the muon. So in the end, I am also fine with large tan beta. So this is, a naive first guess of what might be at work here if I want the solutions. So I will kind of differentiate two cases. One with large masses, order 1 tangent beta, in which the two loop diagrams give you both anomalies. And this is in principle available in both models. And there is a second kind of solution in which you are going to a different regime in tan beta and in the masses. And in that case, you are doing the electron anomaly with two loop contributions and the muon anomaly just with one loop contributions, which is a very peculiar mix that you are doing here. The thing is that, well, I have kind of reason that this is fine in model 1. It's not so clear that one extend that to model 2 because we had additional tan beta dependencies here that were different from the model 1 case. And in principle, it's not guaranteed that it might work. When you do the full analysis that I will discuss in a moment, the fact is that, well, this second peculiar region is absent in the second model. So in one model, you have two different regimes. In the other, we are just confined to this, restricted to this large mass regime. Now, of course, this is just a kind of reasoning that you might expect that, but you need to do a proper analysis. So the analysis that we did was, well, full numerical analysis, analyzing parameter space of this model, using Markov chain Monte Carlos, driven by a likelihood. Well, there is a typo here, there should be a minus. Likelihood which is defined in terms of some chi-square function, which typically for most observables is just a comparison of your expectation with a measurement over an uncertainty. You include all your correlations. If something is asymmetric, that is not exactly Gaussian, well, you do the usual thing. But this is not for all your constraints because some of them are peculiar. For example, you have bounds, so a few modifications, those observed, you should implement. And of course, you need your shopping list of relevant constraints. First, of course, you want to reproduce those anomalies, which is your first and main ingredient. And then you need to put some additional requirements. Constraints in the scalar sector, fermions, Higgs measurements, other low energy constraints, something coming from LEP, and also from some LHC searches. So let me just flash a moment some details about this. For the anomalies, you want to reproduce this. So the natural constraint would just be, well, make your chi-squared with the central values and the uncertainties that you read here. But this has a downside, which is, well, just moving less than 3 sigmas from these values that you want to reproduce. Well, you may lose one of the anomalies. So you set one, I mean, a prediction which is 0, the other is still 2, 3 sigmas away. So this some kind of divert your numerical analysis into a regime in which you are not really reproducing both. So we do something which is much more stringent, which is, well, instead of using this natural chi-squared, we do something which forces you to be really, really close to both central values, which is just taking it, well, if it's within a very small value of the minimum of this chi-squared, fine, 0 instead of what it was. But if you are outside that small ellipsis, then you have to, it's kind of an infinite well in which you are forced to be on top of those values, which is something that I illustrated with just a small plot. Those are the individual values, central values and the uncertainties. Well, in the plot that I will show later, I am forcing my numerical analysis to lie in this small region, which is definitely far, far away from the standard model point, which would be deviation 0 in both one. No, 0 is here, sorry. So you are definitely way out of this region. For the remaining constraints, well, in the scalar sector, your usual requirements are bounded potential, perturbativity is respected, electroweak precision in those oblique parameters. You also require your Yukawa couplings to remain perturbative. For the Higgs, you put the usual production times decay signal strength, gluon fusion, vector boson fusion, etc., and your decays. WW, GC, BB bar, etc. And since on top of that, you are playing with large lepton couplings, you also need to put the pieces of information that are available for final mu plus, mu minus, and E plus, E minus decays. Then, of course, you need further constraints related to processes in which you can substitute a W gauge boson with these charge scalars, since some of them are quite well measured, like purely leptonic decays, or some of those semi-leptonic decays involving some pseudoscalar meson, some additional flavor stuff, also information from LEP, since you measure cross sections up to a center of mass energy of those 200 and something GeVs. And this mainly just pushes the masses of the new scalars above that threshold. And since there are searches at LHC, well, dilepton searches, typically with gluon fusion production, and also some searches involving the charge scalar. So you collect all those constraints, implement them, and crunch your numbers. So I will show some results in which, just to stress the importance that the LHC searches have, I will just show together regions that you have when you do not impose them, and the final ones in which you have imposed that. There is also a footnote on this, which is, well, if you keep your scalar potential with the exact symmetry, as it happens, your scalar masses are bounded from above, so this would eliminate one of the solutions, the one with heavy masses. And it would also not allow large tan betas, which would kill the other solution. So this means that, well, the scalar potential with the exact symmetry is not good. So you really need to have some breaking of the symmetry. So that's why I included it from the beginning when I wrote down the potential. And since I have mentioned that, well, you have the two kinds of solutions in this first model, but one of them is absent in the second model, I will just show some results for this model. In the regions that are present in both, well, you can read there, and the ones that are just present here, you also have. So just flashing a few of the plots that summarize the results of the analysis, you see that, well, the regions in the two most relevant parameters, well, fall into what I was expecting. It's not so clear, but this linear relation that comes from the two loop contributions, one can kind of guess. And the range of values is in agreement with what I had anticipated. And then the other branch, which corresponds to muon anomaly at one loop and the electron anomaly at two loop. And you see that, well, those muon couplings are large. We were expecting that. And the electron couplings can be as small, let's say, as a few GeV. In terms of how those parameters correlate with tan beta, this just confirms what I had anticipated. One region around tan beta 1, and the other requiring very large tan beta values, and the corresponding thing for the muon couplings. I have not even mentioned what we are doing with the third lepton, with the tau. And the thing is that it's not, the information here is non-trivial in the sense that, well, when you want to see which is the region available for this second solution, you see that it's something is at work with the tau lepton. For the first solution here, the tau does not care. You can do that with any values, but here it's not that irrelevant, since well, sorry, since you might be spoiling part of the contributions that you need in order to produce that. And this is something that naively, in our first analysis, in our guesses, well, is completely absent, of course. If you now take a look to how these new couplings correlate with, for example, the mass of the scalar, you see more or less what you were expecting. One branch in which this guy is light, and the other in which it can go heavy. And you see that, of course, the couplings to the electron are, as we were expecting. In one case, they remain rather contained, while in the other, that is can be kept quite large. And similarly, what you were expecting for the muon. And next, sorry. If you want to take a look to what happens, a more complete picture of what is going on in the scalar sector, well, you see the allowed regions in terms of the different combinations of masses. And this is also along the expectations. Well, I will not insist much, but well, in the end, these at large masses, you are typically expecting that they are quite close in mass in order to pass the electroweak precision constraints. And that also sets some peculiarities here in terms of having either the pseudoscalar and the Charles scalar or the scalar and the Charles scalar quasi-degenerate in order to avoid those electroweak precision constraints. But apart from that, these are the regions that we were somehow expecting. Same thing when you want to see what happens in terms of those masses and beta, which is not so shocking. And in order to see what was the importance of the LHC constraint, you have noticed that, well, I was always plotting here darker region, which corresponds to the final result, and another one in which I had just removed the LHC constraints, and in fact the solutions, the final allowed solutions, are disjoint. Well, this is because you have, for example, here that your you have here, for example, these resonant searches at LHC, which cut through these regions, leaving you just with two branches, one for each solution, which are disjoint. And this is why in previous plots, at the end of the day, your two solutions are not connected continuously. So this shows you how important are those LHC constraints. and in fact that they are actively constraining these kind of models when you want to reproduce the anomalies. One can also take a look to the dominant decay channels that, well, when one wants to understand a little bit of the details behind all of this is relevant, but I will not bother you with this. Same thing for the different scalars. The only thing that is peculiar and maybe worth mentioning is that, well, decays into leptons are typically the most relevant one, among the most relevant ones, since we are putting those quite large couplings. Of course, since the coupling to the top quark is the mass of the top, apart from those tangent beta factor, there is a regime in which, well, that would be, of course, as you could expect, the dominant decay. And the only oddity here is that in some cases you may have this pseudoscalar decaying to scalar and Z, which has an important role since this is going to suppress other branching ratios and will help you to avoid LHC constraints by diluting the branching ratio in the case of this guy into muons, taus, etc. Because, I mean, your worry is that since pseudoscalar production cross-sections are larger than scalar production cross-sections, you might run into trouble with this pseudoscalar. And this helps avoiding that situation. I mean, this is for a charge scalar. And of course, there were also constraints for the charge scalar production and decay, but as you see here, they were much less relevant since they are not even touching the regions in which one could potentially explain the anomalies. And just as a final bonus, well, since we are putting quite sizable lepton couplings to scalars and pseudoscalars, one can see, well, how is this kind of E plus E minus going to muons? How is this cross-section looking if I'm going beyond LEP energies, let's say at the ILC or something like that? Well, the couplings are huge in this solution region, in one of those solutions, the one with light masses. You are close, or you are within range. So what you would expect is to see huge resonances showing up. So this is just the ratio of that cross-section over the electroweak one. The electroweak one is more than 90% is channeled a photon. Well, here you are increasing that by several orders of magnitude on top of the different masses. These are just a few examples. To see that, well, at least one of those solutions with this kind of weird couplings is something that is quite falsifiable at E plus E minus going to mu plus mu minus facility. So this was all. So just to summarize a little bit, well, seeing that within this kind of two Higgs doublet models, which have just a couple of properties that are nice in order to try to address those anomalies, that is that in lepton favor universality in the couplings of those new scalars is going beyond just mass proportionality, and this is an ingredient that that you need in order to explain the anomalies. And the other, let's say, theoretical good property is that this kind of scenario in the lepton sector with general flavor conservation is stable under the renormalization group evolution. Well, these two models can address those anomalies with a scalar sector that is just like in types 1 and 2. You need to introduce some breaking, otherwise you run into difficulties. And the thing is that you have two types of solutions I have been discussing with different characteristics. One, let's say, heavy masses, similar vacuum expectation values, that is tan beta border 1, and two loop contributions giving both the anomalies, and a more peculiar exotic solution in which you may have light scalars. This is only available for one of the models. You have a definite hierarchy in the vacuum expectation values, and then you are not reproducing both anomalies with the same kind of two-loop contributions, but just one of them, the electron, while for the other, you are fine with just one-loop terms. So that was all, and thank you very much for your attention.
Thank you, Miguel, by the nice presentation. So now we open for the questions of the audience. You can type the questions in the chat in Portuguese or in English, I can read, or just turn on your microphone and ask directly to Miguel. So maybe I can start. I have a question, Miguel, about the model. So you impose as a two symmetry in the potential, right? But in the Yukawa, you keep it general.
Yes.
With the assumption that the extra matrices are diagonal. Is that it?
Yes. The thing is this is not completely consistent, let's say, in the sense that if I had imposed a symmetry for the complete Lagrangian, I would have had to impose it also for my lepton couplings. And that would mean just taking one of those two Higgs doublet models of types 1, 2, X, or Y, which are the four possibilities that you have when you impose, for example, a Z2 symmetry. But what I have done here is focus, let's say, in this other property, stability of that kind of structure under the renormalization group evolution. Of course, if you have a kind of texture of structure which is imposed by a symmetry, well, then you can count on the fact that that will not be spoiled perturbatively by that evolution. The peculiarity here is that this kind of diagonal structure, because your neutrinos are massless, is preserved even if there is not a symmetry which is enforcing it. So you are somehow mixing two ingredients. I mean, I know that a Z2 symmetry with imposing this guarantees that the thing is stable under the renormalization group evolution. Well, this, in principle, is not guaranteed to fall in that, I mean, to have that nice property, but as it happens, it is stable too. So we just go for the simplest mix of these two ingredients. I take the simplest situation. I mean, I could just go into more general scenario in which I could take diagonal couplings of up quarks, of down quarks, unrelated to the masses, and also more general thing for the leptons, and repeat the same thing. But of course, there the parametric freedom that I would be using would be much larger. So I would completely lose an intuition about what is happening, because I could, in general, I could just switch off some quark terms or not. The fact here is that I am constrained to have this kind of quark couplings, and that is absolutely non-trivial. Since, for example, one of the solutions, just switching from one model to the other, is unavailable. So if I had kept a more general situation, where I could play more games, but the thing is that would not be that well defined under this kind of consideration. I don't know if that satisfies your...
No, yeah. It was just to get it right. What is the framework you were working on? But yeah, I see.
Yeah, I let's say we are allowing enough freedom to address these anomalies, but not too much. I mean, not taking too many liberties, let's say.
Okay.
Just allowing this in the lepton sector, and not introducing new parameters in the quark sector in addition to that.
Okay, I have a question from Clarissa. He asked about if you assess the estimatives from high luminosity or high energy LHC in your analysis, prospects from the LHC at, I don't know, 27 TV or with high luminosity.
Can you? I have another one. What was the question? If we had estimates on that, or?
Yeah, if you had have an analysis about the impact that high luminosity or high energy LHC would have in this model, in constraining the model.
No, we have not done that, but what one could somehow expect is that this kind of, similar curves, of course, since, well, here the bounds that were imposed are those curves. I mean, the data here, in real data, in fact, stopped here at 1 TeV, but we kind of naively extrapolated that. Well, extrapolated, it's too complex a word because we just kept that last value as a bound, which is of course better than nothing. And the thing is that you could see that this kind of measurement is already eliminating quite a lot from what you would naively expect as regions in which you can reproduce both anomalies. So of course, if you keep pushing here, that is assuming that you are not discovering a thing, obviously. Because if you discover something, fine, bingo, this is very nice. I have the all 750 GB business again, a lot of excitement. But well, imagine that is not the case. You are just improving your bounds. You can see here that if you start to lower this curve, you might even completely eliminate the large mass solution. So for example, if you take kind of a complementary view, LHC could completely eliminate this branch, and you would be left with and that is the very weird thing, that you would be left with a very exotic situation in which the other solution survives. Fine, but the other solution is something that could not survive measurements at the plus and minus machines at high energy, because there you would have huge peaks. So definitely high luminosity LHC, by pushing down this thing, carves down a lot of parameter space. But actual numbers to reflect that we have not implemented.
Okay, Clarissa had another question, but it seems that was just answered. It was about this plot, right, Clarissa? I think you just answered by explaining.
Tessio, could I ask something?
Yes, go ahead, Paul, please.
Okay, I have a more general question. We have this problem with G-2 of Muon for some decades already, and it seems very difficult to settle. And now we have the G-2 for the electron because of those measurements of alpha and QED and so on. Is there any kind of, can we expect that this is going to be settled soon, or it's going to take as long as the Muon G-2, which is not already settled too? Is going to stay this problem, or it's just a problem people are not caring about?
Well, I would like to have a crystal ball to really know what is going to happen, but in the end, mean, it's just when you think about those two anomalies together that you might start to worry. Sure, I mean, the Muon one has been there for a lot of time, but this is just at 3 sigma, and you have all this hadronic vacuum thing, and which I'm not an expert, and for the electron is not even at that level. So
maybe it could take longer to.
Yeah, it could take longer, and the thing is that I would not expect that that it gets more more critical in the sense that absolutely new physics is clearly needed here.
Okay.
You know,
just one more. Okay, I can go.
Yeah.
Okay. You mentioned that the CP violation in this model could have some kind of problem with the electric dipole moment, or you're just not touching it?
No, the thing is that if I can do two things. I mean, if I keep the model in full generality, I have these couplings here which are complex, and having those couplings there complex, let me just go one moment to my backup slides, because in full generality, your Yukawa, your couplings look this way. I mean, this is the mixing matrix of the scalars, and the thing is that when you have your full mixing matrix and those n matrices are in general complex, you can see that you will have scalars and also pseudoscalar couplings. So this is a sign of CP violation. So if those things were in general complex, I would have CP violation, and this would mean that I will have also contributions to the electric dipole moment. Of course, of the electron, of the muon, of the tau, but the electron and the tau, who cares? They are very poorly measured, if measured. Instead, with the electron, it's very, very, very critical, because you have this very stringent bound with 10 to the minus 29 electrons per centimeter, I think, which is 1 second over here. So the thing is that if I keep my model in full generality, this constraint will tell me that, well, if you want to have simultaneously an imaginary and a real part, you will have to reduce one of them quite a lot. So that will push me into something like this simplified regime. This will force not much mixing in the scalar sector, or not the simultaneous presence of scalar and pseudoscalar couplings of the leptons. But in principle, since I am in a larger parametric situation, that is no problem. What I have done is, I'm simplifying my analysis, and I'm going into a regime in which I will automatically skip these problems.
Okay. But in summary, you could have, you could explain it, explain the G-2 and still be in accordance with the
electric dipole moment. Absolutely. Because by construction, in this simplified regime, there is no contribution to the electric dipole moment.
Thank you. Thank you for the nice talk.
Welcome.
Further questions for Miguel? I have another question, Miguel, more technical one. About the chi-square analysis, you said that I don't get the idea behind the how can I say? Yes, in this slide, you use the not the first.
Yeah, let's say not the natural. Yeah, the thing is that if I just use this chi-square here, which is sorry, because here I forgot to include that these C's are the central values, and these sigmas are the uncertainties. which is the natural thing. So that would be the chi-square that one would naturally use. So that would mean that the ellipses in that chi-square would be, well, the ones that reach the origin here with a value that corresponds to something like 15 in that chi-square. So that's fine to stay away from strictly the standard model. The problem is that you see that by just going a couple of sigmas well, a couple of 2 and something sigmas, for example, in the electron, you are already losing completely the anomaly in the electron. So if I go and crunch my numbers with this naive chi-squared, I would be mixing in my regions, in the allowed region that I plot. If I plot them by going up to 3 sigma, for example, I would be mixing regions in my parameter space in which I'm reproducing both anomalies quite well, but also places in which I am really just reproducing one of them, and the other rather poorly.
So the question is, how do you enforce that you reproduce the electron anomaly with this type of expression?
Yeah, that's the thing. This means that if my prediction is very, very close to the central values, which is what this thing, when this thing is below 1/4, this means that I cannot deviate more than half a sigma in one of them, and in another direction is a combination. So this means that, for example, if I am right on top of the anomaly for, let's say, the muon, in the electron I cannot deviate more than half a sigma here. So this is the way in which I'm just saying that, well, I am allowing just a region very, very small around the anomalies. I'm not happy if I am, for example, sitting here, in which, yes, both values are different from the standard model, but it's not that we are looking. I mean, you have a deviation, but you are somewhere in between the experimental values and the standard model. No. What I'm saying is, well, beyond any reasonable doubt, I am putting here a model that gives non-standard model predictions of both observables.
Okay, I got it. Now.
Yeah, it's kind of, I mean, the critical thing would be, well, instead of putting a region, give me just the points in which you get the values. But this is numerically something which is not smooth.
I imagine. Yeah.
So what I'm doing is, first I obtain, to start this numerical analysis, first I obtain points in which I am really reproducing both. Let's say I'm minimizing my chi-squared very close to these values, and then starting from that point, I do not allow my numbers to escape from that region. So that's the thing.
Very nice. So any else questions? No? If not, I think we can stop here. I would like to thank again you, Miguel. Thank you very much for accepting the invitation. Thank you for the nice presentation.
Thank you very much, Tessie. It was my pleasure. Sorry that I went overtime, I think.
No, don't worry. And thank you guys who attended this presentation. And that's it. See you next time.
See you. Bye-bye.
Bye-bye, guys.